Welcome everyone. Today, we'll discuss pipeline integrity, focusing on two critical threats, stress corrosion cracking or SCC and corrosion fatigue. These mechanisms can severely impact pipeline safety and reliability, so understanding them is essential. Pipeline integrity is the backbone of safe energy transportation. In this session, we'll explore why integrity matters and dive into SCC and corrosion fatigue, two major challenges in pipeline operations. Pipeline integrity refers to the ability of a pipeline system to operate safely and reliably throughout its intended lifespan. It encompasses structural soundness, resistance to environmental and operational stresses, and compliance with regulatory standards. Maintaining pipeline integrity is critical because pipelines transport essential resources such as oil, gas, and water over long distances, often through challenging environments. A failure in integrity can lead to catastrophic consequences, including environmental pollution, economic losses, and safety hazards for communities. The concept of integrity management involves continuous monitoring, preventive maintenance, and timely interventions to mitigate risks. Stress corrosion cracking or SCC and corrosion fatigue are two major threats to pipeline integrity, as they can cause gradual deterioration and sudden failures if not properly addressed. Understanding these mechanisms is essential for engineers, operators, and regulators to ensure safe and efficient pipeline operations. Stress corrosion cracking or SCC and corrosion fatigue are distinct yet related phenomena that compromise pipeline integrity. SCC occurs when tensile stress and a corrosive environment interact, leading to crack initiation and propagation in the metal. It is often associated with specific environmental conditions such as high pH or near-neutral pH soils and can progress without significant deformation, making it difficult to detect early. Corrosion fatigue, on the other hand, results from the combined effect of cyclic mechanical loading in corrosive environments. This mechanism accelerates crack growth compared to pure fatigue or corrosion alone. Both SCC and corrosion fatigue are influenced by factors such as material properties, stress levels, environmental chemistry, and operational conditions. Understanding their differences and similarities helps in designing effective monitoring and mitigation strategies. Now, let's focus on SCC, its mechanisms, types, and influencing factors. SCC is a failure mechanism that occurs when a susceptible material is exposed to a specific corrosive environment under tensile stress. The process begins with microcrack initiation at stress concentrators such as welds or surface defects. These cracks propagate due to localized anodic dissolution or hydrogen embrittlement, depending on the environment and material. SCC can be classified into intergranular and transgranular types. Intergranular SCC occurs along grain boundaries, often due to segregation of impurities or sensitization, while transgranular SCC cuts through grains, typically driven by hydrogen effects. In pipelines, SCC is commonly observed in buried steel pipes exposed to soil environments with moisture, temperature fluctuations, and specific chemical compositions. Factors such as coating disbondment and inadequate cathodic protection can exacerbate SCC risk. Several factors contribute to SCC development in pipelines. Material susceptibility is a primary factor. High-strength steels are generally more prone to SCC than low-strength steels. Environmental conditions, including soil chemistry, moisture content, and temperature, play a significant role. For example, near-neutral pH environments promote SCC in buried pipelines. Stress levels, whether residual from manufacturing or operational due to pressure fluctuations, are critical in initiating cracks. Protective coatings and cathodic protection systems can mitigate SCC, but their failure or degradation increases vulnerability. Understanding these factors allows engineers to implement preventive measures such as material selection, stress relief treatments, and enhanced protective systems. Next, let's look at corrosion fatigue, how cyclic stresses and corrosion interact to damage pipelines. Corrosion fatigue is a synergistic degradation process where cyclic mechanical stresses and corrosive environments interact to accelerate crack initiation and growth. Unlike pure fatigue, which occurs in inert environments, corrosion fatigue involves electrochemical reactions that weaken the metal surface and facilitate crack propagation. In pipelines, pressure fluctuations and temperature changes create cyclic stresses, while moisture and chemical contaminants provide the corrosive medium. The presence of pits or localized corrosion sites often serves as initiation points for fatigue cracks. Corrosion fatigue is particularly dangerous because it can progress rapidly under fluctuating loads, leading to unexpected failures even in components designed for high fatigue resistance. While SCC and corrosion fatigue both involve the interaction of mechanical stress and corrosive environments, their mechanisms and manifestations differ. SCC typically requires sustained tensile stress and a specific chemical environment, leading to brittle fracture without significant plastic deformation. Corrosion fatigue, in contrast, occurs under cyclic loading and can affect a broader range of environments. SCC cracks often appear as branched or intergranular, whereas corrosion fatigue cracks resemble typical fatigue striations but with corrosion products present. Understanding these distinctions is crucial for accurate diagnosis and targeted mitigation strategies. Detection and mitigation are critical. Let's review the techniques and strategies. Detecting SCC and corrosion fatigue requires advanced inspection technologies. Inline inspection tools, such as magnetic flux leakage or MFL and ultrasonic testing or UT, are commonly used to identify cracks and wall thinning. External inspection methods include direct assessment and hydrostatic testing. Non-destructive testing or NDT techniques like acoustic emission and eddy current testing provide additional diagnostic capabilities. Continuous monitoring systems, including sensors and remote data acquisition, enable real-time integrity assessment. Implementing a comprehensive inspection program is essential for early detection and prevention of catastrophic failures. Mitigation of SCC and corrosion fatigue involves a combination of design, operational, and maintenance strategies. For SCC, applying high-quality protective coatings, ensuring effective cathodic protection, and controlling environmental exposure are key measures. Stress relief treatments and material selection also reduce susceptibility. For corrosion fatigue, minimizing pressure fluctuations, improving drainage, and using corrosion-resistant alloys are effective approaches. Regular maintenance, timely repairs, and adherence to industry standards such as API and NACE guidelines further enhance pipeline integrity. Emerging technologies like predictive analytics and AI-driven monitoring offer promising solutions for proactive integrity management. Real-world failures teach us valuable lessons, and future trends show how technology will transform integrity management. Several pipeline failures have been attributed to SCC and corrosion fatigue, highlighting the importance of robust integrity management. For example, incidents in North America involving near-neutral pH SCC have led to significant environmental damage and regulatory scrutiny. Investigations revealed that inadequate coating maintenance and ineffective cathodic protection were contributing factors. Similarly, corrosion fatigue has caused failures in offshore pipelines subjected to cyclic wave loading and corrosive seawater environments. These cases underscore the need for comprehensive risk assessment, regular inspections, and adherence to best practices. The future of pipeline integrity management lies in advanced technologies and predictive approaches. Artificial intelligence and machine learning are being integrated into monitoring systems to analyze large datasets and predict failure risks. Smart sensors and IoT-enabled devices provide real-time data on stress, corrosion rates, and environmental conditions. Digital twins allow operators to simulate pipeline behavior under various scenarios, enabling proactive maintenance planning. These innovations, combined with stricter regulatory frameworks and sustainability goals, will shape the next generation of pipeline integrity strategies. Let's summarize the key takeaways. Pipeline integrity is a critical aspect of energy infrastructure, ensuring safe and reliable transportation of resources. Stress corrosion cracking and corrosion fatigue are two major threats that require thorough understanding and proactive management. By implementing advanced detection techniques, robust mitigation strategies, and leveraging emerging technologies, operators can significantly reduce the risk of failures. Continuous improvement and adherence to industry standards are essential for maintaining pipeline integrity in an evolving operational landscape.